Hey there guys, Paul here from the engineeringmindset.com. In this video, we're going to be looking at industrial refrigeration system basics with a focus on ammonia refrigeration systems. We'll start at the basics and work our way up, covering some typical systems for single stage, two stage and cascade systems to help you learn the basics of industrial refrigeration. I just want to take a moment to thank our partner Danfoss for sponsoring this video. Danfoss is on a mission to spread as much knowledge about modern, environmentally friendly refrigerants as they can. This includes information about ammonia and how it works in their industrial refrigeration solutions. They have a collection of free ammonia e-lessons available now at Danfoss Learning. Just follow the link in the video description below to start your first course. So where are we going to find these types of systems? Industrial refrigeration applications are typically used in places like cold food storage, dairy processing, beverage production, ice rinks, and heavy industry, these sorts of places. These are large-scale cooling systems. We've previously covered other types of cooling systems for commercial buildings, supermarket CO2 systems, chillers, and chilled water schematics. Do check these out if you haven't already, links are in the video description below. I just want to very briefly touch on why we use ammonia as a refrigerant. Ammonia occurs naturally in the environment, it's available in abundant amounts. It has an ozone depletion rating of 0 and a global warming potential of less than 1. If we compare that to other common refrigerants such as R134A, this has a GWP of 1430, and then R404A has a GWP of 3922. You can see why ammonia is very beneficial to use. Ammonia is also cheap to produce and energy efficient to use. It has the capability to absorb large amounts of heat as it evaporates. That's a really important aspect for a refrigerant to be of use. It also means that pipes and components can be made thinner and smaller. Ammonia is toxic, however, and can also be flammable at certain concentrations. Most refrigerants are odorless, but ammonia gives off a very sour smell, so it's easily noticed if a leak occurs. If ammonia leaks, it will react with the carbon and water in the air to form ammonia bicarbonate, which is a harmless wash compound. Now, for the engineering stuff, let's look at some simplified typical refrigeration systems. Single stage. This is the simplest ammonia industrial refrigeration system other than a direct expansion type, so we're going to start here. We start off with the compressor. This is the heart of the system and is what pumps the ammonia refrigerant around the refrigeration system to provide the cooling. It pulls in the refrigerant that has collected all the unwanted heat from the evaporator and compresses this into a much smaller volume so that all that thermal energy is very tightly packed together, making the refrigerant very hot. The refrigerant is sucked into the compressor as a low pressure vapor and it leaves as a high pressure vapor. The high pressure refrigerant vapor exits the compressor and flows to the condenser. The condenser cools the refrigerant down by pulling the unwanted heat out of the refrigerant and discharging this heat into the ambient outside air. This is typically done by passing the hot refrigerant through the inside of some small tubes and using a fan to force the cooler ambient air across the outside of the tubes to cool it down and carry the heat away. Additionally, we'll often find a small pump spraying water over the pipes. Some of this will evaporate and help carry more heat away. The refrigerant is sealed inside the pipe and does not come into contact with the air or water. It is always separated, the two never meet or mix. Only the heat of the refrigerant passes through the pipe wall and is carried away by the air and water. As the heat is removed, the refrigerant condenses into a liquid. So it leaves the condenser as a high pressure liquid refrigerant and flows to the receiver. The receiver is a storage vessel for a reservoir of liquid refrigerant and holds any excess that's not in use. This allows it to maintain a minimum head pressure and also perform under varying cooling loads, providing a buffer. We'll likely find a line running between the receiver and the condenser inlet. This is just to provide pressure equalization and allows the liquid refrigerant to flow out of the condenser and into the receiver more easily. The refrigerant then flows to the expansion valve, which regulates the pressure and addition of liquid refrigerant into the evaporator circuit. From the expansion valve, the refrigerant flows into the liquid separator. The liquid flows to the bottom and is typically then sucked in by some refrigerant pumps. These pumps ensure correct circulation rates through the evaporators as the cooling load varies. The refrigerant is then pushed to the expansion valves of the evaporator, which regulate the flow of refrigerant into the cooling load. The cold refrigerant enters the evaporator and passes on the inside of some pipes inside the evaporator, and the fan blows the warm room air across the outside of these tubes. The cold refrigerant absorbs the heat, so the air leaves much cooler and thus provides cooling to the space. As the warm air passes across the evaporator pipes, It causes the ammonia to boil and evaporate as a part liquid, part vapor mixture. As it evaporates, it carries the heat away. Just like when water boils in a pan, steam rises from the pan and carries the heat away. Again, the refrigerant is sealed inside a pipe and it never comes into contact or mixes with the air. The two are always separated. The refrigerant leaves the evaporator as a liquid vapor mixture and heads back to the liquid separator. The refrigerant which is liquid falls down and repeats the cycle through the evaporator. The refrigerant which is vapor rises and is sucked back into the compressor to repeat the entire cycle again. The refrigerant enters the compressor as a low pressure vapor refrigerant. Two-stage. This is the next evolution of the industrial refrigeration system, which is suitable for low temperature refrigeration systems, providing high efficiency and low compressor discharge temperatures. We again have the refrigerant flowing the same cycle, but we have a few other components and cycles. In this type, we have a tank called the intermediate cooler, which sits between the receiver and the expansion valve. The main flow of refrigerant passes through the coil inside the tank. The refrigerant passes through this and into the main expansion valve. Just like the single stage system, it then continues its flow via the separator, the evaporator, and back to the separator. Another stream of refrigerant comes off the main line and is sprayed into the tank via an expansion valve to produce a cooling effect. As it is sprayed and evaporates into the tank, it cools the submerged coil. This subcools the main flow of refrigerant inside the coil before it flows to the main expansion valve. The vapor refrigerant being sucked out of the separator still flows to a compressor, but this time we have two compressors. The refrigerant therefore flows to the low stage or booster compressor to increase the pressure. From here it flows and is released into the intermediate cooler, which helps to condense the refrigerant. The vapor refrigerant is sucked out of the intermediate cooler and flows to the high stage compressor, where it will then flow back into the condenser to repeat the entire cycle. Cascade. This is the most advanced system, and these systems can become very complex. It's suitable for refrigeration systems which require different temperature ranges for the cooling loads, and also makes it easier and cheaper to comply with health, safety, and environmental regulations. It is a little daunting when you first look at this system, but if you've watched this video all the way through without skipping, then you should be able to follow how it works. Just give yourself a moment to trace the pipes and see where everything is flowing. These refrigeration systems usually consist of two or more separate refrigeration circuits, often using different refrigerants to provide a cooling effect. In this system, we have two compressors, except they are both circulating refrigerant around separated circuits, a high temperature circuit and a low temperature circuit. Connecting the two circuits is a heat exchanger known as a cascade condenser. We've covered how heat exchangers work as well as the different types in our previous videos. Do check that out, links are in the video description down below. The cascade condenser acts as a condenser for the high temperature circuit, but also an evaporator for the low temperature circuit. The two refrigerants can be the same or they can be different and optimized for each circuit. For example, we could use ammonia for the high temperature side and CO2 for the low temperature side. This would mean that less ammonia is used and the system would be more efficient compared to a two-stage ammonia-only system. I just want to thank Danfoss again for sponsoring this video. Don't forget to check out their free ammonia e-lessons by clicking on the link in the video description below. Okay guys, that's it for this video, but if you want to continue your learning about refrigeration systems, then click on one of these videos on screen now and I'll catch you there for the next lesson. Leave your questions in the comment section and don't forget to follow us on Facebook, Instagram, Twitter, as well as theengineeringmindset.com.